Yeah. That is easy to have happen. Okay. So we've got, okay, good, that's working. Lecture 3.3 today. Methodology for impedance-based circuit analysis. So it turns out we can follow essentially the same algorithm presented in lecture 2.2 for analyzing circuits in steady state with impedance. So remember the method presented in lecture 2.2, sort of algorithm, was going through doing our circuit diagram and our signs, and then our KCL, KVL, our elemental equations, and then we would have to solve a differential equation, right? Do some algebra, do a differential equation. We can do something that's very similar to that with impedance methods, but we won't have to solve a differential equation. So the algebra will be the part that we'll have to do at the end. Instead of being real algebra, it'll be complex algebra, but not too bad. Okay. Good. There are enough variations that we represent it here. So we'll go through. Let n be the number of passive circuit elements in a circuit, which gives 2n, which is V and I, the voltage and the current for each element, unknowns. Here's the method. First, draw a circuit diagram. So same as before. Second, label the circuit diagram with the sign convention by labeling each element with the assumed direction of current flow and voltage drop, right? Okay, same as before. Write generalized Ohm's law for each circuit element and define the impedance of each element. So that's a little bit different. We previously, in step 3, would have written the elemental equation. Instead, we're going to write generalized Ohm's law, which is always V equals IZ, but we're going to write it for, each element will have its own separate impedance, right? So that one's slightly different, but it's the same idea. It's the elemental equation, but like the impedance form of it, right? Which is always just generalized Ohm's law. Okay? Step 4, for every node not connected to a voltage source, KCL. That's step 4 before and step 4 now, so that didn't change. Step 5, for each loop not containing a current source, right? Kirchhoff's voltage law, KVL. Okay, so that one's the same. And you probably have a linear system of 2n algebraic equations and 2n unknowns to be solved simultaneously. So the big difference here is that you don't have any derivatives in there and there's no differential equation to solve. If only certain variables are of interest, so maybe you only care about like the output voltage, then you can eliminate other variables and look for just the one you're trying to solve for. But in general, you can just solve for all unknowns because you have all of the equations you need. So A, eliminate n, or half of the unknowns, by substitution into the elemental equations, using the generalized Ohm's law equations as your starting equation, and then using KCL and KVL to substitute in and eliminate half of your variables. Okay, so that's nice. You can do that. The next step is try substitution to eliminate, to get down to only those variables of interest and inputs. So you are going to have a set of equations left. They're algebraic, so you can solve in any method that you want. So you could do, I'm suggesting try substitution to get down only to those variables of interest and inputs, but you could use elimination. You could use a matrix method using linear algebra techniques. That's all fine. And then solve the remaining system of linear algebraic equations for the unknowns of interest. Or, I mean, you could just start off and say, okay, I've got 2n equations and 2n unknowns. I'm just going to make this into a linear algebra problem and solve it. Linear algebra a lot of it comes down to AX equals B, right? And you can write 6 in terms of AX equals B, and you want to solve for X. So you can either do, some efficient algorithm, or if you just wanted to be, I guess, straightforward about it, X is just A inverse B, and you could just solve just that. So you could just write the A matrix, which is all your coefficients, and then B is everything that doesn't have a variable on the left-hand side. So your right-hand side will be a vector, and then just solve it like that. That's not the most efficient way to do it, finding the inverse, but using Gaussian elimination and back substitution is more efficient, for instance. But however you want to do it. And you can use your calculator for problems that are numerical, but your calculator probably can't do symbolics unless you have some fancy new calculator I don't know about. So if there are symbols in there instead of, say, the capacitance or the resistance of the elements, then you're still going to have to do it by hand. Or you could use a package like Mathematica or Wolfram Alpha. They'll do it symbolically. MATLAB will do it too. It has a symbolic toolbox, and you can do that. If you want to do it in MATLAB, numerically, it's I think that's \B. Yeah. It's the efficient one, I guess. Okay, so this is, that's the method. So this is doing impedance-based, doing phasor-based analysis is almost the same as our previous method, but we're getting away with not doing a differential equation. The gotcha is that you have to use complex numbers throughout this, which, it's either differential equations or complex numbers. You got to kind of choose your poison. And your own adventure. That's more positive. Choose your own adventure. I remember those books. I would always hedge so hard. I'd be like, okay, I'll choose to open the door. And then I would keep my finger in the page though, and turn to page 329, and I'd turn and be like, oh, you died. I'm like, damn it. So I'd go back. and be like, okay, don't open the door. And then continue on. Yeah. I'm sure everybody reads those books like that. They're like, yeah, choose your own adventure. I didn't like that outcome. I remember there was one where it was like get off the boat and try to go through, across the peninsula through the uncharted jungle, and I ended up getting I had ants consume me completely. I was like, wow, that was a bad choice. But also, how did I know that was going to happen? It was almost like life, where you just can't control it. It sucked. Yeah, I stopped reading those books. Okay, so let's do an example, right? Steady state RL circuit analysis with a sinusoidal source. This is the same example that we did in Chapter 2, but we're not going to find the transient response. We don't care about that. Okay, so it's a sinusoidal input. Like before, we had a sinusoidal current source input, and we have a resistor and an inductor in parallel, and we only care about steady state. So what are IL and VL in steady state? So we went through the whole thing before, but we solved the differential equation, found the transient and the steady state responses, the total response. But now we're saying, okay, we only care about the steady state. So we should get the same sinusoidal result that we did before, but this time we'll use a different method. So just to sort of show you, on the same problem, how does it contrast? So Great. So, awesome. Step 1. Circuit diagram. Check. It's already given. Step 2. Somebody mind closing that door? Somebody's projecting out there. Step 2, sign convention, right? So the signs are already given, so we don't really have a choice. Thank you. Appreciate that. Pointed in the same direction as the current, and voltage drop. So 2 is done. 3, we've got our elemental equations, but they're just all generalized Ohm's law in this case. So I'll write elemental generalized Ohm's law. So we can do the same thing as before. We have to write one for each element, right? So we might as well just draw a table again. In this case, we've got a resistor and an inductor, the two passive elements. So L and R. And they're both going to be V equals IR. So VL equals IL ZL. V equals IZ. I don't know if I said R. But. And then VR equals IR ZR. And we should write what ZL and ZR are. Okay, so ZL is equal to, do you guys remember what, so we could either form, we don't have to, decide right now.
Polar 90s.
So omega L, and then it's a 90-degree phase, so pi over 2. Good. And our R, do you remember what the impedance is for the resistor? Just R. Great. Step 3 is done. Okay, step 4, we need to write KCL, KVL equations. So KCL for nodes that are not connected to a voltage source. So remember, this is the one where we had redundant equations, right? So we have a node up here, we have a node down here, and they have the same equation. So we only really need to write one of them. We have the IS, so all the current going in is equal to all the current leaving, right? So IS equals IR plus IL. That would be one way to write it. So IS, everything going in, equals IR plus IL. And step 5. KVL. So we have a current source, so we don't need to do that loop. But the other loop, tells us that VR is equal to VL, right? VR equals VL. Good deal. Okay, look at this. We're already on step 6. So, this took us like, I don't know, 4 minutes maybe to get to the point where essentially all that's left is just to math it, right? So, once again, it's the math part, and I know that it's not trivial, and I don't mean to make it sound trivial, but the math part is to some extent automatic, right? We could automate this. We could teach a computer to do this. So to really make sure you're getting these problems, getting steps 1 through 5 right, that's getting the circuit analysis. You have to be able to do the math in step 6. You have to do that. But the new stuff, the real like actual circuit analysis you're learning, is done by step 5. And it's actually, when you use this sort of systematic approach, it's not too bad. Break it down into small, manageable chunks. Okay, so in step 6, we need to math. We need to solve. Specifically algebra in this case. And so we have, how many unknowns do we have in this circuit? So we've got 2 passive elements, right? So for each passive element, we have a voltage and a current that we don't know. So each passive element provides 2. So 2 passive elements and 2 unknowns each gives us 4 unknowns. So we have 4 unknowns and 4 equations. And I like to use this step 6a, eliminate half of the unknowns by substituting in KCL and KVL equations into the generalized Ohm's law equations. That's a great way to start, knocking out half of your unknowns. So let's do that. We can eliminate 2, and we kind of have our choice. It becomes less clear which variables are interesting to us and which ones aren't interesting to us in this formalism. Because remember, in the past, we were like, okay, which ones have derivatives, right? Well, nothing has derivatives on it now. So you can kind of just, choose whichever ones you like. Let's choose to, I'm going to write it like this. So we do KCL and KVL, and we're going to take those and put them into the Ohm's law equations, and we're going to, by doing this, we're going to eliminate 2 variables. Let's choose 2. So let's hear from the audience. It's like, whose line is it anyways? IL. So we're going to eliminate IL, which we can do, but I'm going to suggest we don't do that because we want to solve for it, right?
We can eliminate both V's very closely.
Both V's very quickly. Okay, so we're going to do a little bit differently than we did in the last one. We're going to do the 2. So, but we also want to solve for VL, right? So I guess we can do it, but we want to solve for IL and VL, so we kind of don't want to get rid of them. We could, and then at the end, we solve for all the variables, and we could back substitute.
Can you answer that by finding the equivalent impedance? Like doing the parallel between R and L?
Maybe, but we're trying to avoid shortcuts for now. We're trying to just do general, always apply the whole method. There might be shortcuts for this specific circuit, but I want to show you guys a method that works for any circuit that you're going to see. So I guess what I'm saying is we can eliminate any variables we want, but we probably shouldn't eliminate the ones that we want to solve for, because then we got to go back and find them later. So
let's do IR.
Okay, so IR, let's eliminate IR, and then we can choose another one too, right? So we can eliminate IR, and we could choose VR, or we could choose, VR would be the other one that's not one we want, right? So let's try VR, for instance. Okay, so let's eliminate those 2, and let's do so. Let's look at our L and our R equations again, our Ohm's law equations. And so we're going to get rid of, so VL is still there, right? And IL is still there. So this one is still VL equals IL ZL. This other equation, though, has VR equals VL, right? So VR, we're going to get rid of, oh wait, sorry, it's this one. VR and IR. So our KCL equation tells us that IR is just IS minus IL, right? And that VR is VL. So we can rewrite this as VL on the left-hand side, substituting in for VR. So that became VL. And then IR is going to become IS minus IL. And we still have a ZR, right? ZR. Great. So that came from there to there. So we now have two equations in VL and IL, right? As our two unknowns. And so we can solve those as well. So it's really easy to just set them equal to each other, right? The two VLs. And then solve for IL, right? That's probably the easiest way to go to start. So let's do that. So B. So let's do L equation equals the R equation. Or IL ZL equals IS minus IL times ZR. Okay. Get the ILs on one side, so we'll add ZR IL to both sides. Factor out an IL and divide both sides over, so or just divide the remainder over. So that's what we have. IL equals. So it's going to be ZR divided by ZL plus ZR times IS. So there's one of our unknowns, right? Solved for. In terms of IS, which is an input, so that's good. And then the impedances, which are all knowns. Now, we can do all of this without plugging in what these Z's are, right? We should probably plug in what the Z's are at the end. So I will try to be explicit when I ask you in problem statements if you need to or don't need to explicitly express it in terms of what the impedances are. Maybe I'll say like in terms of omega, where omega is your frequency of your input. So you have to actually explicitly express it in terms of omega. So let's do that. Let's plug in for this one what our impedances are, and then even the input too. So let's plug in all of those and see what IL is. This is one of the things we're solving for, so we might as well do it, right? Okay. So we know it's there. All we need to do is just like sort of simplify, which can get a little messy. This is the part that gets a little messy sometimes. So ZR is not messy, right? That's just R. ZL, we can use either the rectangular or the phasor form, and we're going to be adding it to the ZR component. So which form should we use? Rectangular, right? Because when we add them, having the rectangular form is better. When we multiply them, it's better to have the phasor form. So rectangular form, and so the rectangular form was just J omega L for the impedance of the inductor. plus ZR is just R times IS. So we need to write IS as a phasor. It was given in this non-phasor form, right? Trigonometric form. So we got to write it as a phasor. And it's a sine, right? Not a cosine. So we have two options. We can either use the unconventional sine phasor and say, like, using sine phasors in this problem, or we could introduce a 90-degree phase shift to the sine term. So I always have to look at a unit circle to decide if it's. I think we should do the cosine convention for our phasor because it's the one that's, I would say, a little harder. So let's do that. Let's use the cosine one just because we're given a sine. If we just barrel forward with the unconventional sine phasor, then we don't have to do as much work. So let's do more work because we've got time, right? And it's Wednesday. So I always look at the unit circle, and I have to say that cosine term is 90 degrees behind the sine term, right? So if I was to write IS, whoops, cool, puppet warp, skip this tour. Okay, so if I was to write this as a phasor, if I was to write IS as a phasor, well, maybe it's first best to, instead of skipping right to a phasor, let's write it as a cosine. So it's going to be A times cosine of omega t, and then we got the phase shift, right? So is it going to be plus or is it minus 90 degrees? Let's try minus pi over 2. If you get confused, like I always do with this, then I just plug in a number and see if it works, right? So if omega t is 0, then if it was the sine, we would expect this to come out as 0, right? So cosine of negative pi over 2 should be 0, and that works, right? If we went to positive pi over 2, we should get 1 out of the sine, right? And so we go to positive pi over 2, we get pi over 2 minus pi over 2, and we get cosine of 0, which is 1. So we're good. So it's minus pi over 2 was the sine, was the phase. I can't memorize anything, so I just always go back to this stuff and just try stuff out. I always say, I don't get smarter and I don't remember more things as time goes on. I just get better at debugging. It's like the one thing. I've seen the debugging path a lot of times, so guess and check. So if this is the trigonometric form in terms of cosine, then what is the phasor? It's A e to the what? Minus, so j pi over 2, right? Minus j pi over 2. Great. So we've got our phasor form. So let's plug in our IS now. So it's A e to the minus j pi over 2. So we can simplify that, right? So how do we, so there are two ways to go here. We could turn the denominator into a phasor because we're going to divide, right? Or you could do the complex conjugate thing to rationalize that complex fraction. It's up to you. Let's do the phasor one, just because that's probably good practice, right? So let's turn the denominator into a phasor. So the numerator will also turn into a phasor because we're going to divide, right? It's r e to the j what? Well, 0, right? I'm not going to combine it with this. So I'm just going to leave r. So r e to the j is 0. So there's no phase for r, right? So, but divided by, now I need to write this as a phasor.
Root square r square plus omega l square.
Yep. So the real part squared plus the imaginary part squared. So that's the magnitude.
E, J, tangent, R.
Yeah, so it's the tangent of the imaginary over the real, right? So it's going to get a little messy if we write that in. I think we should just write in like phi1, okay? Just so that we don't get too messed up. We haven't used phi yet, have we?
No.
Okay, so j phi1. And we could probably write this as like m1 or something like that. Probably would simplify our expression. Great, and we've got a e to the minus j pi over 2 out here still. Cool. We're taking our time on this? Yeah.
I'm sorry, just real quick.
No, good.
What is phi again?
Phi1, oh, we should write what phi1. Good. So where we've defined, so def phi1 equals the arctan of the imaginary part over the real part, which is the omega L over the real part was R. So we were just making this into a phasor, the rectangular into a phasor. Good. Yeah. So now the magnitudes combine just by division, right? So we've got the magnitude as R over, yeah, so I should have probably called it M1, but R squared, square root of R squared plus omega L squared, and so that's the magnitude, right? The phase is, so remember when you divide exponentials, you subtract the denominator exponent from the numerator exponent. So you get e to the what? Minus j phi1, yeah. So 0 doesn't contribute to that summation. But when you go to the numerator, you get a negative sign from the denominator exponent. And we still have a e to the minus j pi over 2. We're writing out all the steps here. We'll get faster at it as time goes, but it's good to slow down at first just to make sure you've got the idea. So now we can multiply these two phasors. We got a magnitude and a phase, and then we got a magnitude and a phase. So the a multiplies by the other amplitude. So we've got AR divided by square root of R squared plus omega L squared. So that's the magnitude. And then our phase is E, and then we just add these two phases, right? E to the, you could say minus j phi1 plus pi over 2. Awesome. So this is the phasor form of one of the things we're looking for, right? IL. We could convert it back to trigonometric form now, right? So we know that this is equal to, in trigonometric form, AR over, whoa, that was a big one, over square root of R squared plus omega L squared times cosine omega t
minus E1 minus E2.
minus pi over 2. Good. And we then see kind of like the somewhat silly fiction we went through by converting it over to cosine, because now we can convert it back to sine if we wanted by just saying, oh, well, cosine of something minus pi over 2 is just sine of something. So AR over square root, whoa, of r squared plus omega L squared times the sine of omega t minus phi 1. So these are all three pretty good simplified answers. But we should be able to transform among them.
I can use the polar one as well, right?
You can use the polar one too if you wanted to write like with
Just
the angle.
yeah.
Yeah, you could use that too. That's fine too. It depends on your notational preference between the E one and the angle one. Yeah, if you like the angle one, that's totally cool. So yeah, those are all good answers for IL. Okay. Now we also were asked to solve for VL in this, right? So we could go back and solve for all of our unknowns, but we really only care about VL, right? We have IL, so if I look back to even back to our original generalized Ohm's law, if you have IL, VL comes by just multiplying IL by ZL, right? So I just use this equation. And so let's just do that. And let's use our final result in the phasor form, and then it'll be a lot easier. So we have that from Gen Ohm's law. VL is equal to IL ZL. And IL we said was this, right? So let's rewrite that. AR divided by the square root of R squared plus omega L squared. And it was times e to the minus j v1 plus pi over 2. And then we need to multiply it by ZL, which are we going to want it in the rectangular form, or are we going to want it in the phasor form? Phasor form, because we're going to multiply it by a phasor, right? So that's preferred. And so that is, we wrote at the very beginning what ZL was, right? In that form. It's omega L e to the j pi over 2. So let's write that here. Omega L e to the j pi over 2. So we can just multiply the magnitudes. So the magnitude of the result is ARL omega divided by the square root of R squared plus omega L squared times e to the, and then you just add the exponents, right? So we have a plus pi over 2 and a minus pi over 2. So we just get a minus j phi 1. And that's the phasor form of our result, right? So depending on what's asked, this could be the answer you give. I don't know why I can't draw a straight line today. I'm holding shift on purpose to draw a nice straight line, but like, there we go. Usually I'm on my game, but not on my game today. But we could rewrite this as a trigonometric form, right? So the same amplitude, ARL omega, and r squared plus omega L squared. And then we're going to do cosine of what?
Omega t minus v1.
Excellent. Great. And we could do the sine form too, but that seems sort of superfluous at this point because you'd have to add in a pi over 2 ad hoc at the end. So, okay. So that was the whole thing. I mean, we could do a sine. You want to do a sine? Let's do a sine.
The normal one sine, no?
Yeah, let's do a sine. ARL omega r squared plus omega L squared.
Sine omega t minus v1.
And then is it plus?
No, the cosine has a minus.
Minus.
No, in the cosine, because the original source is sine. So
Yeah, but we were using the cosine form of the phasor, right?
okay.
Yeah, so if we wanted to write also, so when we converted it back, we could just use directly the cosine. If you want to use the sine version of the phasor, then we would have come back to sine, right? But we used the cosine, so we came back to cosine. So then we would need to add pi over 2, right? This is, yeah. So, I mean, this is also valid. If you wanted to write it, because the original one was in sine, so it's kind of nice to go back to seeing it in sine.
We can change the angle as well.
Can change the what?
The angle, so we can always get the source to angle 0, and the other things that has angles.
Yeah, I mean, I think that it's probably good at first when you're doing these to not mess with the source's phase. Just stick with the original source phase. So, I mean, when you're working with steady state, typically the phase, the absolute phase, isn't a big deal. So if I say the input is sine omega t, and you're only looking at steady state, you probably don't care that it's sine. You could just use cosine. But it's good when you're first learning this to just use the definitions and get used to it. And then you can start to recognize, oh, okay, in steady state, I don't care about the absolute phase so much. I just need to start off the source at 0 phase, and that's fine. So yeah, you're right that it's in steady state, it doesn't really matter that much what the absolute phase is, just the relative phase from the beginning to the end. So oftentimes we'll start with just a 0 phase, just because it doesn't matter. So it's just like our initial time is usually 0, because it could be anything. So, okay, cool. Any questions on this? Okay, and then question. Good.
So I am confused as to how you phased something that is not sine and cosine.
So if you have, So the phasing, the one time we did that here was in the denominator. We had this j omega L plus R, and we turned that into this, right? So we took this term, draw a box around it, and we made it into this term. So we phased that, right? I'm going to give up on straight. There. So that box became that box. So we phased that. Rectangular into phasor. And so that's always it always looks like real. So I'll do, I don't know, A plus JB. And that's always equal to square root of A squared plus B squared times E to the J, and then arctan of B over A. So there's that type of phasing it. There's also going from trigonometric form, it's the sine or cosine, into phasor form. So that one, if you've got cosine of omega t plus psi, if you got like a cosine omega t plus psi, that's just going to be in phasor form a e to the j psi.
I didn't understand that one, just not the.
Ah, this one. Got it. Yeah. And yeah, maybe it's worth, maybe I can try to draw like a map of like all the conversions from like rectangular to phasor and then trigonometric to phasor. Yeah. I know, it gets a little confusing, right? But there are only like a handful of them, so you don't have to remember an infinite number, just like a handful. Okay. I'll see you guys on Friday.